In this unit, we will look at the kinetics of disinfection. We can model disinfection kinetics with a first-order reaction. So this is a simple first-order reaction where we're modeling the concentration or the number of organisms at any time as a function of a constant and time. Schick's law was developed in the 1920s. It was later refined to include a concentration term here that showing that the level of disinfection, the efficacy of disinfection is also dependent on the concentration, and that is typically described as to the nth power, which we have a coefficient of dilution, a dependency both on time and concentration, not surprising. Now, if C is constant, then this becomes K prime, and we now have a first order reaction again. So if C is constant, then we can multiply the product C to the nth power times K. That gives us K prime. It's a new constant, and we have a first order reaction. This is the whole concept or the basis of what we refer to as the CT concept, which we'll be talking about in more detail. This is a plot of the log, so we could do it log of N over N naught. So the number of organisms at any time divided by the initial number of organisms and the natural log of that, or the log base 10, either works. And what you see is what we have, the yellow line is our first order decay. So that is just ln of N over N naught is equal to minus KT. So that's the first order. What we observe, though, is that that is often not the case. So we may have a situation here, as I've shown in red, which is the multi-hit, and it's referred to as shouldering. It kind of looks like a shoulder. And what you see is that initially the decay rate is slower, and then it increases. Potentially what's happening here is we could have, for instance, diffusion limitation. So it takes a period of time for the disinfectant to actually diffuse into the cell. We need a threshold concentration, and then once that threshold concentration is reached, we start to see more effective inactivation or death of the organism. We also can observe what's referred to as retardant, and I've shown that here in green. And what you see there is a more rapid decay initially. So perhaps these are more susceptible, these are more resistant. So that's one possibility. We could also be running out of disinfectant. So the disinfectant concentration is significantly lower. And therefore, we see a decrease in the rate. Another possibility is that we have hidden organisms. So basically, these are organisms that may be attached to particulate matter. They may be even incorporated into the particulate matter, and that's what makes them more resistant. So we may have a first order. We may have a decay that can be described by the Schick-Watson law, or we may have this much more complicated situation here. we'll focus on the simpler situation and where we can use the CT concept, because that's what is used in water treatment for determining the dose of disinfectant. So in terms of contactors, what we want, especially if we're looking at chlorination, is a contactor that achieves plug flow. And what you see are various different configurations that attempt to ensure that you can see here your water is flowing in this direction, a serpentine direction, so that what we want is we want plug flow. Question was just asked about the retardant curve. Could it be the result of adaptation? Yes. On a short scale, not likely, but on a longer scale, yes. And we see that with antibiotic resistant organisms, that you have organisms that are more resistant to, in that case, an antibiotic. We actually do see the same thing with disinfection, and there's some concern about ultimately, are we producing organisms that are more resistant to disinfection, and how does that play out in terms of treatment? Absolutely, that can be definitely the case. So with contactors, as I mentioned, what we want is we want an ideal plug flow, and we want a length greater than 40:1. This is to try and ensure that we do have plug flow, especially, as I mentioned, with our chlorine contactors. Typically a height to width ratio of 1:3. But what we will use, we'll use this concept of T10 to account for the fact that we have non-ideal flow. And in the US and in a number of other countries, Canada has adopted this, New Zealand has adopted it, this CT concept is used. And it is the log, or the CT that is required for a specific log reduction. And in New Zealand, it's based on the Cryptosporidium. In the US, we'll look at viruses, Crypto, and Giardia. So C is the concentration of disinfectant in the reactor. T is the contact time, but it's actually T10. So T10 is the time required for the first 10% of water to pass through the contactor. And it's often less than 65% of the hydraulic detention time. So for an ideal plug flow reactor, T10 divided by the hydraulic detention time is equal to 1.0. So it's the same. So T10 and the hydraulic detention time is identical. It's equivalent. For a CSTR, the T10 divided by the hydraulic detention time is equal to 0.1. So if we think about this, if we have a hydraulic detention time of 15 minutes in a CSTR, the T10 is equal to 1.5 minutes. So that means that the first 10% of water to pass through the contactor would do so in 1.5 minutes. On the other hand, you think of the plug flow reactor, and think of a plug moving through, okay? And if our detention time is 15 minutes in this, if we have no dispersion, then that plug that we've created here moves through in 15 minutes. It just simply moves as a plug, and the entire plug would leave that reactor after 15 minutes. So this is the concept that we're using with CT. So what we'll do next is we're going to go through an example. There is a Word file that is posted on LonCappa, and that goes through this whole example here. So we have a situation here where, use the highlighter first. We have a town, and they have selected ozone as the primary disinfectant and chloramines as a secondary disinfectant. The pH of the water entering, highlighter does not work very well. So the pH of the water is 7.0. We have a winter temperature of 5 degrees. We will assume a trial ozone dose of 2.5 milligrams per liter. You're given a second order rate constant that was provided based on laboratory testing. And we have a client that would like a contact chamber with superior performance. That means it's close to plug flow. And what you're asked to do is to determine the CT requirements according to the long-term to extended surface water treatment rule. We want to design the contact chamber, and then we'll just determine the feed rate of sodium hypochlorite and ammonia to achieve, and you're given a dichloramine concentration of 1.6 milligrams per liter. Given a design flow rate, and you're told that the water is treated by coagulation, sedimentation, filtration. And the time for the water to reach the most distant customer at the minimum demand, so it's the longest time that would take to reach the furthest customer, is 62 hours. And the plant uses the Verde River. So there's a lot of details in terms of what you're asked, but let's walk through this problem. So the river has very high concentration of total organic carbon. And we worry about total organic carbon because the disinfectant can react with that organic carbon to produce what is referred to as assimilable organic carbon. And that's important because that is typically low molecular weight compounds that can result in bacterial regrowth in the distribution system. The other concern is that that organic carbon can react with the disinfectant to produce disinfection byproducts. And as we mentioned, trihalomethanes are regulated. Regulated as total trihalomethanes. There's 4. And haloacetic acids, and there are 5 compounds there. And we have regulations for those. The other thing we're concerned about is bromide. And that's because bromide can react with water. So this is bromide. That reacts with ozone. So that plus ozone can result in bromate. And bromate is a carcinogen, and it is regulated at 10 micrograms per liter. Now, turbidity, you can see your turbidity is quite high, and so are total coliforms. This is likely after storm events. have runoff entering the river, and that results in higher turbidities and coliforms. And they've done some studies, and they have concentrations of Giardia viruses and Cryptosporidium oocysts in this river system. So the next thing we need to do is we need to determine how much or what CTs are required, or what log removals are required based on the situation we have. We start out with Cryptosporidium. So what we observe, okay, we had greater than 3 oocysts per liter, and that tells us that we need 2.5 log removal that is additional, and this is the difference here. That's additional beyond what we will get in terms of CT credits for the treatment. So we have two different types of treatment here. We have conventional, notice we have conventional filtration and direct filtration. So conventional treatment, we start with screening. Next process would be take the river water, we screen it first. What's the next process?
A rapid mix with a coagulant.
Exactly. So we've got a rapid mix. We're adding coagulant, followed by
Flocculation.
Followed by
Sedimentation.
Then followed by
Filtration.
Filtration. So this is your conventional plant. Your direct filtration plant is, you probably have screening, you have filtration, and you may add a coagulant here. So this is direct. And this is very, very pristine waters. So Lake Superior, for instance. So what do we see? Okay, so we have we have a conventional system. We had greater than 3 oocysts per liter. So we need 2.5 log treatment. That means we need 99.684% removal. 2 log removal corresponds to 99% removal. 1 log corresponds to 90% removal. So the next thing is we'll look at overall disinfection. So what do we need in terms of overall? Giardia, we're told that we have 5 cysts per 100 liters. And that puts us right here at a total of 4 log removal. Viruses, we were told that we had 2 per 100 liters, and that puts us right here at 5. So this is telling us how much overall removal we need. The next step is what we've just done is determined the bin classifications. Now what we need is to determine, based on our treatment, how much credit we get for the removal. So for Giardia, for a conventional plant, we would get 2.5 log removal. For viruses, I don't know why, we would get 2 conventional. For Giardia, we have 2.5, viruses 2. Now crypto 3. But notice with crypto, this is additional treatment. So let's just develop a table so that we've got need overall. For Giardia, we need 4 log removal. For viruses, we need 5. For crypto, we're going to look at additional treatment. So here, add another column for additional treatment. We don't need to worry about that for Giardia or viruses, but we have 2.5 log removal for additional. So this was from table 13-5. This is from table 13-4. The credit we get from the treatment, so from, this is removal in these processes that I've mentioned right here. So it's removal, and we get 2.5 log removal credit for Giardia, 2, and we get 3 for crypto. So from disinfection, we need 1.5 log removal for Giardia. We need 3 log removal for viruses and 2.5 for crypto. And that's because this is what we need, the additional we need. Now, the next thing we want to do is consider how the water quality parameters affect our primary disinfectant choices. So really what we're doing now is we're looking at, are the choices that the client has made? Any questions about this table here?
So you picked 3. Oh, wait. Okay. So I'm just confused with the 2.5 versus the 3 for the crypto.
Okay, so basically the fact that we get 3 log removal credit for the treatment is essentially irrelevant. Okay, we get that credit basically, and what EPA is saying is that you essentially need 5.5 log removal for crypto in order to protect the public. So that 2.5 is an additional beyond what you get for the actual credit from treatment. So that's why this number actually becomes essentially irrelevant, because we need that additional credit. So that's why we essentially ignore it. So EBA is giving you credit, but they're saying, great, you get 3 log removal credits, so that's 99.9% removal of crypto. But in order to protect the public and to ensure that we never have a situation like we had in Milwaukee, where 100 people died and 100,000 people became sick from crypto, that we're going to make you do additional treatment beyond the conventional. So no matter what, you're going to have to do that. So that's where that 2.5.
I think so. So the last column on the right, the needed from disinfection, that's what we still have yet to remove.
That's what you're, exactly. So what we'll do is we will use that, okay, to determine the dose of disinfectant. Let's go through it, and hopefully it'll make more sense as kind of we go through the exam. Okay, so the next thing we're doing is we're looking at how does water quality affect the choices. And so we're attempting to, in this case, confirm, are the client's choices reasonable? So the first thing is we'll look at TOC. Now, we were told that the TOC of the raw water was 10 to 20 milligrams per liter. With this kind of water, you're likely to do some disinfection early in the process, and possibly even between screening and rapid mix. So let's start here. So we start there. The first question we're going to ask is, do we have high TOC? Your criteria is greater than 2 milligrams per liter. And this is in our untreated water. We had 10 to 20, absolutely. So the answer is yes. The next question you're going to ask is, do you have high bromide? The criteria there is greater than 0.1 milligrams per liter, and that's of bromide. And we had 10 micrograms per liter, which, so the answer is no. So we can go here. What that tells us here is that we have a high disinfection byproduct formation potential because of the high organic matter. Because of that, we would want to use ozone with some sort of a biological activated carbon to reduce the potential for biological growth in the distribution system and the formation of disinfection byproducts. We could also use chlorine dioxide or UV. Notice, because of this, if we had high bromide, we would eliminate ozone. And we eliminate ozone because of the formation of bromate. So the next thing we can do is we can look at this in terms of the properties and the ability of the disinfectant to meet the desired disinfection. So we've said ozone is a possible choice. We've said chlorine dioxide is possible, and UV. Those are the three that we're really considering at this point. Now we have Giardia. We need less than 2.0. So ozone is effective. Chlorine dioxide is effective, so we don't eliminate either, and so is UV. We look at crypto. Crypto, we needed 2.5 log removal. Well, ozone is effective, chlorine dioxide is effective, and so is UV. So we haven't eliminated anything yet. Viruses. We need greater than 2 log removal. So we needed 3. Same thing, we can achieve that. We haven't eliminated. So based on this, all 3 of the processes are still essentially in the running. We can also look at other issues, for instance, the production of trihalomethanes with TOC. Now, I will disagree with some of this table, but that's okay. With ozone, it says S for slight. The reason for that is you don't produce trihalomethanes with ozone. You produce trihalomethanes if you ozonate, and then you use chlorine to provide a residual in the distributions. All 3 of these are okay. You produce oxidized organics. And this is why we need the BAC, the biologically activated carbon. Halogenated organics, again with ozone, where we form that is if we use chlorine as a disinfectant. Bromate is our big issue here, but bromate's not an issue. BOM is biologic or biodegradable organic matter. And yes, that's an issue. As I mentioned, this is why we would look at a BAC system, a biologically activated carbon system. So this just provides us some guidelines to know whether or not we should eliminate which disinfectant. So ozone's still in the running. We haven't eliminated here, so it's a reasonable expectation or selection. We can also compare the disinfectants in terms of the process. So we're looking here at ozone and chlorine dioxide, and we're looking at ozone. Again, I would disagree with some of what's in here. There are safety concerns, and that is true with ozone and chlorine dioxide. In terms of process control, it's stated developing for ozone. Europe has used ozone since 1896. I have a hard time seeing that as developing process control. Back 30 years ago, there were only, actually more than 30, 40 years ago, there were only 3 plants using ozone in the US, but now there are hundreds of plants using ozone in the US. So I would say process control is well developed at this point. Same thing with UV. UV, it's a little bit newer, but it's, I would say, developed. And that's a question we can, when we have the engineers from Black and Beach come in and talk to us more about UV disinfection, they'll talk and really discuss process control for UV. So the next thing we want to do is consider the secondary disinfectant. AOC, again, is assimilable organic carbon. So the first thing is, do we have high AOC? And yes, we have a high TOC. And if we really do want to consider how to remove disinfection byproducts, how to prevent regrowth, so we'd look at a biologically activated. The F here is for filter, activated carbon. Do we have a high disinfection byproduct formation potential? Again, we have that high TOC, so the answer is yes. And here we're looking at something, probably activated carbon. We may want to use enhanced coagulation. And that's just a method to try and reduce the disinfections in the distribution system. Do we have extended distribution time? This is a question. It's greater than 48 hours. We have 62. So what that tells us is that we want to look at either chlorine or chloramines as our secondary disinfectant. Major thing is noted here is you want to make sure with chloramines that you don't have excess ammonia because of the potential regrowth in the distribution system. So we're now to the point of starting to actually use this information in the design. We're going to continue with ozone. We haven't eliminated it. We have pH of 7. We will design the system for the lowest temperature. And that's because your rate of inactivation is lowest at the lowest temperature. We have a rate constant. Typically with ozone, you're going to need more than 10 cells. And the diffuser is in the first cell. So that's where you're adding your ozone. And according to the textbook, we have some optimal ratios for height to length, width to length ratios. And your height for these are a very deep basin. And that's because, if this, we're going to think of this as a column, our diffuser is at the bottom of the column. We're adding ozone from the diffuser. And what we want is we want a significant depth where we can allow the ozone in these bubbles to dissolve. Now, the client asked for superior performance. So that means we will have a baffled reactor. We have a perforated inlet baffle. We've got serpentine or perforated intrabasin baffles where we have cells. So that makes those baffles will divide the cells. We'll have an outlet weir or a perforated launders. And again, this is to try and ensure that we have as close to plug flow in this reactor as we possibly can. So the next thing we want to do is determine the CT requirements. EPA provides a number of tables. These tables are from the appendix. It's Appendix D in your book. They're actually from the Code of Federal Regulations. So they're codified by EPA. We have a temperature of 5 degrees, and we needed 2.5 log removal for crypto. So that means we need 40, and notice the units here are there. Think of it as milligrams per liter times minute. So this is C times T. For Giardia, we needed 1.5 log removal. The textbook doesn't have a chart table for 1.5 log removal, but we'll look at the 3, and we have 5. Looking at ozone, we have 1.9. And actually, I've provided you a table here, elsewhere. So you can see for Giardia, 1.9, we need 0.95. So we actually need 0.95 milligrams per liter. So that's for viruses, we need 3 log removal. This is 4, so we'll use this table. It gives us a higher value than we really need. That is 1.2. And then actually, if you look at the other table that I provided you, we needed 3 log removal and 5 degrees, we need 0.9. So it's actually, so just looking here, we have 40, 0.95, and 0.9. So removal or inactivation of which organism will control disinfection?
Would it be the one with the greater?
Exactly,
CT?
it's the greatest. So in that case, it's Cryptosporidium that controls disinfection. Looking at this, can you see why in New Zealand they simply eliminated any consideration of Giardia and viruses and said design your disinfection system based on crypto? Does that decision make sense? It does, because if you just look at ozone and you compare for no matter what temperature, if we look at 3 log removal here, we look at 3 log removal here, our ozone still controls disinfection. Okay. It's the highest value. I've just provided a couple additional tables just to provide you some additional data. So the next thing we'll do is we want to use the pilot plant dose to determine CT and T naught. So T10 divided by tau is equal to 0.7. That's for superior performance. We need a CT of 40 milligrams per liter minute. And we were told to start with a 2.5 milligram per liter dose as the trial. So if we start there and we have T10 is equal to 40 milligrams per liter minute, we divide that by 2.5 milligrams per liter. We're dividing by the concentration, and that equals 16 minutes. The detention time is then T10 divided by 0.7, that's 16 divided by 0.7, and that equals 23. We then use the equation for second order decay. And this is just the integration of a second order reaction to determine the concentration. And I've got a table down here. So what we need is this has to be 40 milligrams per liter. So what I've done is I've iterated on a solution. Okay. And the Excel spreadsheet for this is provided on Kappa. So in this case, 2.5 wasn't going to give me 40 milligrams per liter. So I adjusted both the hydraulic retention time and T10. You'll use the equation C equals C naught over 1 plus KT C naught to determine the residual. So this here is what I'll use to determine the residual. And I'm going to use the hydraulic detention time. When to determine CT, I'm going to multiply my residual by my T10, and that gives me this value here. I will add up all of these to ensure that the sum of the CT values is equal to the requisite CT value that we previously calculated. So we'll use the 2.9 milligrams per liter. We have a flow rate of 30,600 cubic meters per day. There are 1,000 liters per meter cubed and 10 to the minus 6 kilograms per milligram. And that is equal to 88.74 kilograms per day. So this information allows us to size the ozone generator. And the way ozone generators are purchased is actually on the mass of ozone that they can produce per day. So now we can look at sizing the reactor. So if we have a hydraulic retention time equal to 28 minutes, so we get 10 cells, each 2.8. That gives us a total hydraulic detention time of 28 minutes. So the volume of the reactor is just our detention time times Q. So it's 28 minutes times 30,600 cubic meters per day. And that is equal to 595 cubic meters. Now, so we've got the volume. Now, in order to size it, according to the textbook, the height to length ratio per cell should be equal to 4:1. So we'll let the height equal to 6 meters. And as I mentioned last week, here we want a very deep basin because we want to ensure that we have as much mass transfer of that ozone from the gas into the aqueous phase. So these tend to be very deep. So that would give us a length of H/4 or 1.5 meters. So that's each cell. The volume is then equal to the height times the length per cell times the number of cells times the width. So our height is 6 meters. Our length per cell is 1.5 meters. We have 10 cells, and this is equal to 595 cubic meters. And that would give us a width equal to 6.6 meters. So the dimensions of the reactor is 6.6 meters wide by 6 meters deep by 15 meters in length. The last part that I asked you to calculate was the feed rate of sodium chloride and ammonia. And in this case, you're asked to determine a dichloramine dose of 1.6 milligrams per liter. So if we add ammonia and hypochlorous acid or sodium hypochlorite, what we would form first is the monochloramine. If we add additional hypochlorous acid or sodium hypochlorite, we form the dichloramine. So this is mono, and this is the di. So for every 1 mole of ammonia that we have present, we need 2 moles of hypochlorous acid or sodium hypochlorite. So we're just going to write this as ammonia plus 2 OCl, and that is going to result in the formation of dichloramine. And we want 1.6 milligrams per liter. So we need to convert the 1.6 milligrams per liter to a molar units, and we have 1.6 milligrams per liter, and that's our dichloramine. That has a molecular weight of 85.92 milligrams per millimole, and that is equal to 0.0186 millimoles per liter. So in terms of the dose of ammonia, we have 0.0186 millimoles per liter, and multiply that by the molecular weight of ammonia times the flow rate times 1,000 liters per meter cubed. So liters cancel, meters cubed cancel, millimoles cancel, and we'll convert to kilograms. So milligrams cancel, and that gives us 9.7 kilograms per day of ammonia. So that's how much ammonia we would need to add. Now, since the problem stated that we were adding sodium hypochlorite, not hypochlorous acid, we'll use the molecular weight for sodium hypochlorite. Remember, we needed 2 millimoles of sodium hypochlorite. We'll multiply by the molecular weight of sodium hypochlorite. And we do the same set of calculations. And we need 59.8 kilograms per day of sodium hypochlorite. So that gives us both the sodium hypochlorite dose that we need, and it gives us the ammonia dose we would need in order to achieve this 1 milligram per liter of dichloramine.